in the bioengineering department and works very closely with the Health Sciences Center. He's one of the individuals, along with Dana and a few others, who've been really kind of on the leading edge of doing a lot of computational related work, and both at the educational and the research level. And it's been a pleasure getting to know Kendall over the last year and a half, and I look forward to actually meeting him sometime in person in the not too distant future. I do hope at some point you can share with us what your dissertation on global shape function models of an underwater explosion bubble is all about, because that just sounds very interesting at so many levels. But maybe you can get to that, maybe you can't. I'll save that for questions at the end.
Sounds good.
So with that, Kendall, take it away.
I do want to
and I'm gonna
interject that we are recording this so that everyone in the room is aware.
Yeah, and I also was going to say, we like questions. So as we're going along, if you have a question, throw it in the chat, and we'll call on you. Tammy will call on you. So.
And I like questions in the middle of everything. In other words, I'm okay with just stopping and answering a question right away. So I will. That's the way I'll approach this. So this project really shows my background in mechanical engineering as much as it shows my more recent work in bioengineering. It's a collaboration between, there's Priya, who is actually, I just noticed, joined the Zoom. This is her master's work she did with me. And then Pene Joan is the physician at Children's Hospital that has provided the data and provided us with clinical insight on how to use this data. And then that last person, Kendall, is me. So it's a collaboration between Children's Hospital Colorado and the University of Colorado, which is what most of my research, if not all of my research is a collaboration between clinicians and engineers. So to start out, I'm just going to talk through, I've got a couple of slides that are more background. And these may be a little simple, but I just want to make sure everyone is on the same page. I've been thinking about the circulation now for about 15 years, but some people aren't thinking about it every day. So I want to make sure we're all there. So of course, there are two circulations. There's a systemic circulation, which we're used to thinking about, and it's fed by the left ventricle. So the left ventricle pumps out blood through the aorta, it goes through the body, it returns through the vena cava into the right ventricle ejects through the pulmonary artery, which splits up into the two lungs, and then that returns through the pulmonary vein. When we think about measuring pressure, you've probably all had a cuff on your arm, and that cuff on your arm can measure pressure in the systemic circulation, but to measure pressure in the lungs requires a catheter. It requires invasive access, just to get that out right away. No one likes to be cut. Well, anyway, most people don't like to be cut. So we try to avoid invasive measures, and I'll talk a little more about the future. But in general, also the systemic circulation, it's a big circulation. It takes more pressure to move blood through it. And its healthy pressures are from 10, actually this is in the ventricle itself, from about 10 millimeters of mercury to 120 millimeters of mercury. If you're not familiar with millimeters of mercury, I'll tell you that 760 millimeters of mercury is 1 atmosphere of pressure. So what this is much less, like 1/6, 1/7 atmospheric pressure is enough to move blood around our whole body. And then the lungs take much less pressure. They take 5 to 20 millimeters of mercury to move blood through them. And when I say that, I'm saying a maximum of about 20 millimeters of mercury in a healthy patient. So a second background slide, I'm just going to note that the ventricles that supply blood to the body, they're shaped quite differently. The left ventricle, which is this red mesh you see here, is approximately a truncated ellipsoid. And I say that, kind of laugh when I say that, because that's engineer speak. I don't think a clinician would say truncated ellipsoid, but that's, we want to be able to model the shape and know what it's typically like, what kind of coordinate system we can measure it in. And it's a truncated ellipsoid. And in that sense, it has symmetry planes. And because it has symmetry planes, when we are using a two-dimensional imaging modality, we can sometimes just get one plane. We can just image it along one plane And that's enough to really know what's going on. On the other hand, the right ventricle is like a glove that wraps around the LV. It's a crescent shape when it's looked at from above. So if I look at it from this V and ventricle down, you would see the LV as this circle and the RV as this crescent that wraps around it. It's non-symmetric. It's hard to image in a single plane. And in general, it's just not as easy to describe as the LV. So the final background slide is that I'm going to note that the LV has location-dependent deformation. So when we talk about, excuse me, the RV has location-dependent deformation. So the RV has two walls in general. It has a free wall, that is to say the wall that is not in contact with the LV. So that's the part that would be in contact with the lungs. And then it has the septal wall, which is, of course, the interventricular septum. And that interventricular septum is typically considered to be part of the LV, not the RV itself. So the free wall mostly contracts in a longitudinal or up and down way. So in this picture, we're looking at it as we might see it in the body. It's oriented such that if we go up from this image, we would go towards the head. And if we go down from this image, we'd go towards the feet. And again, the free wall is the side that we can't see. And it typically contracts up in an up and down or longitudinal fashion. Whereas the wall we see through the LV mesh is known as the septal wall, and it mostly deforms circumferentially or horizontally. So like this. And then indeed the LV itself as an ellipsoid, it contracts, it looks like a pipe shrinking and expanding like this. And then I wanted to note that these directions correspond to the primary directions of myocardial fibers in those walls. So in other words, the LV mostly has circumferentially aligned fibers, and the RV free wall mostly has longitudinally aligned fibers. That'll become important later. So again, that's why I'm bringing this up, bringing up the background. So now, again, a little more background. I study pulmonary hypertension, and pulmonary hypertension is a deadly disease. I say it's a deadly disease because typically when adults are diagnosed with it, they have a life expectancy of 2.8 years. And actually that's the natural history of the disease. Before we had good treatments, it was 2.8 years. Now people are living longer, but they're still dying, and they typically die of right ventricular failure. The reason is let me just say what pulmonary hypertension is. It's written here, but pulmonary arterial hypertension, so that means PAH, is the chronic elevation of blood pressure in the pulmonary circulation. So I mentioned that the maximum pressure most healthy people see is about 20 millimeters of mercury. If you go above mean 20 millimeters of mercury, you have pulmonary hypertension. All of us sitting on this chat, I don't think any of us have pulmonary hypertension. We probably have maximum pressures of 20, and we probably have a mean of around 12. So that's just showing you it's a fairly small perturbation that leads to this disease. And then as people become progressively sick with this, they can have pressures 70, 80 millimeters of mercury, and that loads the right ventricle in a way that it's simply not capable of responding to. And eventually that leads to right ventricular dysfunction, which I'll describe shortly, and right ventricular failure. And as you can guess, failure means it's no longer really pumping blood to the body, and that's a condition in which people die. The way this is diagnosed is a catheter is weaved either from the femoral artery in the neck, or excuse me, the jugular vein in the neck, or the femoral vein in the leg. And they would either come in from above, so jugular access would come in here, right? And then femoral access would come in here, and a catheter would be weaved into the pulmonary artery, and pressure would be read. And that's what's required for diagnosis. That's the standard of diagnosis. Now, on the other hand, people like me, as well as clinicians, engineers and clinicians across the country, those working in pulmonary hypertension, are working on non-invasive ways to characterize the disease and also to track patient status, because you can't and you don't want to catheterize someone every time you want to understand how well they're doing or how sick they are, right? I've got this, my meeting controls have appeared and aren't going away. Okay, anyway, let me look at chat real quick. Oh, raise your hand. Okay, great, went away. Okay, So that's what this talk is going to be largely about, is looking at a new non-invasive way to attempt to track patient status and possibly even prognose or predict the progression of the disease. So let's talk about RV dysfunction. What is RV dysfunction? In a simple phrase, it's when the heart doesn't function normally. So we can define normal function in terms of motions, in terms of changes in volumes, even in terms of deformation or strain. And once we know normal function, when the heart isn't behaving that way, it's in dysfunction. Now, dysfunction is not necessarily bad. It means there's enough flow that life can be maintained, but it's abnormal. And it could mean that there's a disease process going on. And then as dysfunction worsens, you begin to approach failure. And failure is pretty easy to detect. So in these echo images over here, these are 2D echo images. So they present a single plane in the heart. You can see there's very, very little motion where this red cursor is moving. So this is the right ventricle in near failure. There's simply no motion to it at all. And then over here, this is a Doppler image showing velocity. And we see there's still flow, but a clinician would look at this flow and say, "Ooh, boy, this person is very close to failure." Now, like I said, this is easy to see, but early RV dysfunction is difficult to assess. It's difficult to say, is this person really sick or is this person partially sick? Certainly, the heart is pumping enough that they're alive because they're standing here. But the question is, how sick are they? How are they doing? And my goal is to enable earlier detection of RV dysfunction, because earlier detection would lead to earlier treatment and in turn would lead to better outcomes of the disease. So I've been saying deformation, and I'm going to relate that here to strain. And of course, either of these things actually tells us something about how well the heart is functioning, because the heart has to deform to function. If you simply think about it, every time the heart contracts, it reduces in size. It goes from a larger size to a smaller size in order to eject blood. Now, strain is deformation. It's the normalized mechanical measure of deformation. And for those of you that aren't familiar, those of you that aren't mechanical engineers, we have a change in length divided by the original length gives us what's known as a normal strain. And typically clinicians have thought about normal strains in the heart. Now, strain is complex, right? Anyone who's done any solid mechanics or fluid mechanics out here knows that there are 6 independent components of strain. And there are not only normal strains like I've shown here, but there are also shear strains. So I'm going to say the true tensor nature of strain has been neglected so far in clinical analysis imaging, and for good reasons. They simply cannot measure it, but we're going to attempt that today. So get ready. So the way strain is currently measured is with, again, 2D planar echocardiography. So what we have here on the right, for example, is a Doppler image. So again, a red means that something's, actually in this case, it's showing strain values. But in a Doppler image, colors would indicate whether or not velocity was towards you or whether velocity was away from you. So in echo, you can detect echocardiography, you can detect a Doppler shift, and it gives you velocity of a tissue. And then you integrate that velocity to get displacements, and then relative changes in displacements gives you strain. And then you can also collect what I would call, this is known as a cine image. And this is more of is simply a, whoops, went a little far there. This is a brightness mode image that has a, whoops, let me let my slides catch up for a second here. There we go, I'm caught back up. So this cine image just shows brightness of the ventricles. And when you have brightness like this, you can track individual speckles in the echo image. And by tracking those speckles, you measure displacements. And again, relative changes in displacement give us strain. So these are the 2 ways that strain is currently assessed with echocardiography. Now, there are some limitations to those, right? If there weren't limitations, then I wouldn't be giving this talk. I'd just be saying, hey, everything's great. So the limitations include the fact that only normal strains we can find in these 2D views. So typically, clinicians are used to measuring changes in longitudinal strain. So as I move my cursor over this image to the right, the lower image to the right, changes in the lengths of the septum and changes in the length of the free wall are expressed as longitudinal normal strains. And that's all we can do. We can't determine shear strain. We can't determine principal components of strain. We can just get normal strains. Now, again, because the LV is oddly shaped, and because we can only get so much with a 2D image, we can only assess so much strain information in the ventricle itself. So that's another limitation. And then finally, if we assess using a Doppler modality, we can only acquire motion towards and away from the echo probe, right? If there are motions across the echo image, we can't really see those with Doppler because Doppler doesn't pick up, it only can detect something coming directly towards it or something coming directly away from it. That's the only thing that will cause a Doppler shift. All right, boy, you know, I'm used to giving lectures and at some point I say, are there any questions? And I guess I could do that, but there don't seem to be, so I'm gonna continue forward. Okay, so the general reason I'm presenting here is that I believe that we can improve on this 2D strain. And I have a fairly simple hypothesis around this right now, because this is mostly a methods development research project right now.
Kendall,
oh yeah.
ask and ye shall receive.
Okay.
Tom, do you want to go ahead and ask a question?
Yes. Can you have a 3D Doppler that would address that?
Oh yeah, that's where we're going. That's exactly where we're going. Yes. All of this work is based on 3D Doppler data.
How did you get involved in this in the first place?
How did I get involved with it? I was walking around the first floor of, oh no, wait. I think I ran into Penne one afternoon in the offices at Children's, and she was telling me about something called area strain. And I said, area strain, that's not a real mechanical measurement. And she said, it's not? I said, no, show me how you're doing that. And she showed me these meshes and I said, ooh, wow, I can do a lot better than that. So I did.
Okay. So it was literally a walk through a hallway and that got you involved in this.
Yeah, in fact, that's the way I think I've said before that Anschutz is a target-rich environment, and it is. And the way it becomes target-rich is you go visit clinicians and you see what they're doing and you say, oh, wow, that's really cool, but I think I might be able to do more of that than what you're doing right now. And so you do. And usually it works, or sometimes it works out, sometimes it doesn't.
All right. Thank you. Go ahead.
Sure.
Let me ask one related, Kendall.
Sure.
Has the pandemic put a kibosh on that?
Oh yeah, I didn't go into Children's Hospital for like 16, 18 months. Yeah, I wasn't in there at all. And I've only started to go back recently.
Interesting.
Yeah. I mean, I've done a lot of Zoom meetings with clinicians and that's been helpful, but it's not the same. Right. So yeah, and there's a bar on Anschutz campus called Ursula. And I've started to meet one of my former students there, and sometimes he brings along clinicians, and that's helpful too. Okay, so back to the talk. So as a bioengineer, I have been taught that I always need to hypothesize something about the work that I do, which is not really an engineering thing. It's more of a scientific thing. But I've become used to that. I need to have a scientific hypothesis, and my hypothesis for this work is that my three components of what I call 3D surface strain, and I call it that because I don't want people who are familiar with strain know that strain in a plane can be, well, it exists in the plane, but then you can rotate that plane in any orientation and you get 3 dimensions possibly in which the strain is acting. But if I were to say 2D strain to a clinician, they would say, oh, like the 2D strain you're getting from a 2D echo image. And I say, no, it's not like that. So I had to make up a new name for this. I call it 3D surface strain. So it's in plane strain in a 3-dimensional mesh. That's what I'm going to measure. And I expect that the components of this, as well as which are going to be longitudinal and circumferential strain, as well as the shear strain, as well as the principal components of strain that I'm able to compute, they will differ between healthy and diseased populations. So when you think about that, I'm saying at the end of this, I'm going to do a t-test, or I'm going to do an ANOVA statistical test. And I expect that I'm going to have groups of healthy and sick kids, and the strains that I compute are going to be different between them. So that's not a very high mark at this point, but I've never done this before, so I've got to start with something. So I start with that. That's my hypothesis. And one reason that the reasons that I would think of this is because currently longitudinal strain is assessed in the disease, again, from 2D echo, and it is proven to be fairly useful in tracking patients. It just has the limitations that I've already noted. And then shear strains, we found some articles that suggest that they may be associated with cross fiber shortening, and that is something that changes in disease. So the second reason we would expect to see changes between populations is we expect that shear strain would also change in disease. Okay, so I'm going to go through this like a grant, and actually I have recently written a grant and submitted a grant on this. So the grant had 3 aims, and it asked 3 questions. The first was, can I actually compute strain at all? I mean, that's basically what number 1 says. Number 2 says, is that I have this mesh, and this mesh is over the entire right ventricular surface. Can I partition this mesh using mesh curvature? When I say partitioning, I mean, I want to create regions within the mesh. Like I have the septum, and I would want to distinguish the septum from the free wall. And then going further, I might want to look at septum close to the top of the heart or towards the bottom of the heart. So I want to create regions in which I can track strain. And I want to do that using curvature of the mesh. And then finally, I want to look at the principal components as well as other measures and look at how they change spatially and how they change temporally, and whether or not that will actually enable earlier detection of ventricular dysfunction. And of course, this one is going to be the hardest, and I haven't done it yet, but you know, this is a work in progress or presentation, so I'll show you how far I got. So number 1, can I actually do this? First question. And I'm going to tell you, yes, I can. If I hadn't, I wouldn't be presenting. So let's go for it. Okay, so what you see on the right is not a simulation. This is actually a mesh acquired and post-processed from 3-dimensional echo. And it's pretty amazing that imaging modalities can do that these days. And each node in this mesh is represented as a registered point on the heart in the tissue that is tracked over time. So if I have this mesh of, as you can see, triangles, and the nodes of these triangular elements or cells represent real positions in the tissue that are moving over time, I have exactly what I need to compute stress or to compute strain. And most amazingly is that I didn't perform a simulation to get this. I measured this. So my overall process is this, and hopefully I'm going to go into more detail in the next few slides. Hopefully that's not too much detail. But briefly, I'm given meshes in what's known as unstructured cell data format. And I have 12 to 40 meshes per patient. What that means is I have meshes over the entire cardiac cycle. So I see the heart at end diastole when it's largest, and then it contracts to end systole, and then it expands again to end diastole. The first thing I have to do is project the elements into their local coordinates. And in that projection process, I remember that my end, not my end systolic mesh, my end diastolic mesh, when the heart is its largest, is considered the reference or undeformed state, and all others have deformation. So the heart is going to get smaller. And as a result, all my strains will be negative. In other words, the heart is going to shrink in contraction. And I'm sorry for this mistake, not in systolic, but rather in diastolic fashion. Once I have elements in their local coordinates, I can use finite element methods, strain displacement relations, to compute my local strains. So in each one of these triangles, I will compute a local epsilon XX, epsilon XY, or epsilon YY, and then my shear epsilon XY, which is 1/2 the actual engineering shear strain. And then from those, I'll also find my local longitudinal circumferential, my longitudinal circumferential strain, and my principal components. I'll project those back into 3 dimensions, and then I'll output VTK or visual toolkit meshes for post-processing in ParaView. So that's the brief overview. And now I'll go into somewhat more detail. I haven't presented to engineering audiences in a long time, so I can't remember how much detail to include. Like, I would not show this to a clinical audience because they would say, what are you talking about? And no offense to them. Oh my God, these people are brilliant. But, you know, they're not mathematicians, so I wouldn't talk about it in this way. But each step I'll briefly go over. So projecting the elements into 2D, I basically have a single element, and I first find the element normal. And I do that by taking the cross product of the 2 element sides. So if A is my node 1, B is my node 2, and C is my node 3, I form the vectors BA and CA, and I take their cross product, and that's my normal. I always take BA, this vector here, as my local x-axis, and then I form the cross product between this normal and BA to find my y-axis. So that's how I establish my local coordinate system for each element. And then to project data into the system from 3D, I would take any point in the 3-dimensional domain. So I could take C, and I take, for example, I take the vector CA, so a vector from 0, 0 to C, and I dot it with the unit X and the unit Y vectors, and that provides me local X, Y coordinates. And what's really convenient about this is that it automatically ignores any free body modes, the 3 translations and the 3 rotations that could occur to this mesh that have nothing to do with deformation. And as you saw from the previous mesh, this heart does some translation, and the meshes, the individual elements of the mesh can undergo some rotation. So by projecting into this local system for each element, I just ignore those, because it's really just the motion of the 3 nodes with respect to each other that tells me what the strain is. Okay, I then use standard isoparametric triangle strain displacement relations to find the strain. And these are a couple images that are copied out of Carlos Felipa's book. I don't know if you're familiar with Carlos Felipa. He taught at the University of Colorado. I took finite element methods from him in the mid-90s, and he was on my committee. So whenever I do finite element work, I have to cite his references. So, and he did a great job. So these are the matrix equations that describe how to convert the displacements of the nodes here, these UX1, UY1, and differences between the nodes in the reference configuration to actual strains. And then this is 1 over twice the area of the element. So this little charmer gives me the strains, and it gives me, again, local XX, local YY, and local XY strains. I then perform 2D strain transformation, right? This is something I teach in biomechanics. So local 2D or just 2D strain transformation, just rotation of this now 2-dimensional tensor in the plane. So I can find a rotation angle either by knowing what direction the longitudinal and circumferential axes are in each local coordinate system. And again, I'll just say, I don't know that I've explained this enough, but the heart, the mesh itself, typically from what's known as the base, where the valves come out of the heart, to the bottom of the heart, or apex, that's the clinical term, base and apex, that's typically longitudinal direction. And that's actually that's also from head to toe in the body. So I can project that direction into local coordinates, and I can find local longitudinal and local circumferential directions, and I can get an angle from that. And then I can also find the principal angles using this equation right here, and you'll find this in any undergraduate textbook. And then I simply perform the transformation using the tensor form of rotation of coordinates. To project back into 3D, I then take these 2D local directions and I recompose them from my local XY vectors in 3D, and I scale them. And that's how I get 2D components back into 3D. And then my shear directions, I don't project, because shear typically is represented as motion. It's represented as an angular change. I wasn't really sure how to represent an angular change in my post-processing code peer review, so I just had it as a magnitude. And then finally, I also retain the directions of my principal components and the angle of my principal components with respect to the longitudinal direction, which is more or less straight up, straight down from the head to the toes. And the reason I'm going to do this is because I'm interested in whether or not these directions change in disease. Okay, so that's all my details. So then the first step is we validated this, and Priya developed these meshes, and she basically gave them uniform 5% normal directions in the Y direction and the X direction. And then she rotated them arbitrarily in 3 dimensions and translated them arbitrarily in 3 dimensions, right? Because in the projection process, all that information is just completely ignored, as it should be. And what we found is that our technique it worked well. It computed strain within 3% of the expected results. So that means if we gave uniform 5% strains, we recovered strains of like 4.98%. So we did really well. And in each case, the shear strains were 0, as we expected them to be, given that we only applied normal strains to our test validation meshes. So before I actually show what this looks like in patients, I'll just go through my patient cohort. So right now, I'm working with a patient set that has 1,346 unique images. And let me just tell you, this is an absolutely massive pediatric imaging set. I mean, I am so grateful to Pene for collaborating with me. She has done an enormous amount of work collecting these images in kids. And she's very interested in how to use 3D echo to improve these kids' lives. So I hope that this work will also help her towards that goal. It's actually on not 1,346 patients, but rather on 302 kids with pulmonary hypertension and 61 kids that are controls. And these kids would come into the clinic because they had chest pain or they thought they had a heart murmur, and they would undergo echocardiography. But at the end of the day, they were fine, thank goodness. And as a result, we have these 3-dimensional meshes of their heart that we can use to say these kids have no dysfunction. This is what we expect to be normal. Because we're in a pediatric hospital, you would expect most of our kids to be young, and indeed that's the case. The 50th percentile, the median age of these kids is about 14.5. The 75th quartile is 19. And again, this is current age, so some of these meshes were obtained 4 to 5 years ago, so the kids have aged since then. And there are some older patients, so there are older adults with congenital heart defects, still living with congenital heart defects, that come in and get imaged. So our oldest patient in this cohort is 49 years old. And then finally, the data I'm going to show today is not from this 1,346 image set, but it's from a preliminary image set that Pene provided me to do, or provided to us, Priya and I, to do development. And it's 61 controls, so it's all the controls. It's 54 kids with what's known as associated pulmonary arterial hypertension, which means they probably have congenital heart defects that have given them pulmonary hypertension. And then 57 idiopathic pulmonary hypertension. And idiopathic is a fancy way of saying we don't know what's causing this. So idiopathic pulmonary hypertension is really the worst form of the disease. It's just, it develops, and we're still not exactly sure why it develops. All right, so some results. So everyone loves a good 3-dimensional animation of the heart beating, don't you? I mean, come on, this is some cool stuff. But when we look at this, what we see is arrows that represent the actual strains themselves. And this is the maximum principal component of strain. So I get the 2D strain, and then I find the principal components, which are essentially the maximum and minimum strains in the plane, in any orientation in the plane. And, oh, they stopped animating. They're supposed to keep going. And the first thing we can notice is that, of course, the magnitudes in the control subject are quite a bit larger. But then secondarily, we notice that there's much more longitudinal arrangement of the strains in this control patient. And this is what we would expect, because this patient's free wall should contract primarily in the longitudinal direction. And if I run this again, these are kind of slow animations, but you see there is some motion here that's circumferential, but we have these large areas of we have some circumferential deformation here, but primarily longitudinal deformation here. But in the PH subject, we see this large area in which there's primarily circumferential contraction. And this has been presupposed that as the ventricle is subjected to higher loads, that remodeling, in other words, the cardiac tissue would remodel and try to adjust for the larger loads by contracting more circumferentially. And what this method has shown for the first time is we've measured this. We've actually measured the degree of circumferential contraction in the RV free wall. And you may not remember, but typically clinicians look at an imaging plane that's from top to bottom in the RV. So they don't see circumferential contractions at all. They only see longitudinal strain. And they quantify dysfunction in terms of how much longitudinal strain has reduced, but they can't look at how much the strain has moved, at least the principal components of strain have moved from longitudinal to circumferential. And that's one thing that I'm really pressing this method as an advantage over traditional 2D methods. So that's really the end of AIM 1. I asked whether or not we could do this, and the answer is yes, we can. Any questions? Okay, it looks good. All right, so let's move on to AIM 2. And AIM 2 is...
Let me ask a question,
Sure.
Kendall. So you're looking at kind of the general kind of a system view of it. If you were to pinpoint and say, are there certain areas where it's more important than others to look at, or key indicators? Could you?
You nailed it, man. You totally nailed it. That's what AIM 2 and AIM 3 are about. Yes, I want to partition the surface into various regions and then track strain regionally, and then see whether or not there are specific regions that really speak towards dysfunction.
Okay.
Cool. So this second aim is really developing those partitions. And we primarily use computational geometry. When I say computational geometry, I just mean we're doing geometric stuff on a computer because we have this mesh, and I don't want to do this by hand. Ooh, goodness. So I do computational geometry. I do geometry by computer. And my algorithm is it is an algorithmic approach. It's not statistical or machine learning based. I may bail or try to bail to a machine learning based approach if this does not work. But for now, I simply cut the RV circumferentially, that is in a horizontal plane. And what you see here is a vertical plane, actually. So this is a vertical plane shown, this gray plane. I'm going to be cutting it horizontally, and I create two-dimensional contours of the RV. So where the RV surface is cut, I track that and I create a contour. I then find the areas in this 2D contour where the maximum 3D curvature occurs. And the reason I'm interested in maximum 3D curvature is because the LV imposes itself into the RV and it creates this hollow. And it's a good way to find the septum. So as you can see in this image, these areas, this is where the septum actually meets the left ventricle, and it's the regions of highest curvature. So by finding these, I can identify the septum. And then finally, I orient the mesh in a way such that I know where the septum is in my three-dimensional space. And I will again slice this 3D surface in order to partition it into a variety of regions in which to track strain. So then a little more detail on that approach. I mentioned the base of the heart and the apex of the heart. I will again state that the base of the heart is where the valves come out, and it's close to your head. And the apex of the heart is the bottom pointy part of the heart that points towards your feet. And fortunately, that direction in my meshes is already well established. It's primarily along the global z-axis. So I don't need to really orient the heart a great deal. It's already oriented from top to bottom, but I may need to rotate it such that the septum points in the way I want the septum to point. And again, to do that, I create these 2D slices. So I slice the LV mesh circumferentially, and I find regions of maximum curvature. And as you can kind of see in these, I'm noticing that my my slides are zoomed in. That's unusual. Are you seeing this too? Let me get out of this and just.
No, it's not zoomed in. It's.
Oh, it's not? Okay. Huh. I don't know why that's what I'm seeing on my, okay. That's really interesting. That's what I was seeing on my, my view that I'm watching this presentation on. So these 3 points represent the areas of maximum 3D curvature. I connect them. And then I see whether or not the lines connecting them are convex. In other words, they move away from the centroid of this 2D shape, or they're concave. So they move towards the center of this 2D shape. And if they're concave, that means they're the septum. And so I'm able to find the septum this way algorithmically. Then I find the three-dimensional normals within this plane, or within this, along this curve, and I find the average normal direction. And then I orient the entire mesh such that that average normal direction points along my global Z direction, or excuse me, my global X direction. At that point, my septum is pointing towards positive X, the top of my heart is pointing towards positive Z, the bottom of my heart is pointing towards negative Z. And then after that, and this has not yet happened, I will again slice the heart and I will create 15 regions. And this is the work of another set of researchers who are not doing strain, they're doing something else, but they have devised this region system that I am also going to use in order to find regional strain. And then once I create these regions, I will label nodes, or I will label elements according to the regions they're in, so that when I actually compute strain, I can then collect them. I can say, okay, well, this is the strain of this element, but it also belongs in this region. So I'm going to add it to a list so that I can do statistics on this particular region later. Questions about that? I hope I explained that well. Maybe it was not as complicated as I thought it was. Okay, so moving along. And so far, I've successfully created 4 regions, or 5 if you count the valves. That is to say, this light blue area right here is the free wall. And of course, elements are not quite, they don't form a perfect line. So you can see this jagged line of elements. And anything that is light blue has been labeled as being on the free wall. Anything that is dark blue has been labeled as being on the septum. And then this light gray area at the bottom is the apex. And then at the top is the base of the heart, of course, where the valves come out. And then my current algorithm is comparing cell normals. And it's saying if a single element or cell has normals next to it and other cells that are nearly identical, it's on a valve because the valves are almost perfectly flat. And that is giving me some error. So there's these red elements that are really in the base are being identified as being on the valve, being on a valve surface. And I'll fix that over time. But nice. The algorithm works great. I have these 172 meshes, and it found the septum and free wall with 100% accuracy. So this suggests that this algorithmic approach is working. I will test it on a larger set of meshes, and I'm sure it's going to fail somewhere. But if it works 99% of the time, I probably will not use a machine learning approach. I'll just use an algorithmic approach. All right, so that's actually the end of aim 2. Tammy just made an announcement. I'll address that at the end. So the third question, or the third aim that is part of this research, is whether or not only really the principal component directions of strain and magnitude shows group-specific spatial and temporal variation, but whether any of the new strain measures I just computed have spatial and temporal variation that enable more rapid detection of ventricular dysfunction. And of course, why do we want earlier detection of ventricular dysfunction? Because the earlier we can detect this, the earlier we get a patient on therapy or some other intervention, and the more likely we save them from a poor outcome. And a poor outcome can be something from heart transplant to death. So we definitely want to improve outcomes in this disease. So aim 3 is mostly statistics, and I say temporal PCA, which is temporal principal component analysis. And principal component analysis is a type of machine learning. If you're familiar with eigenvalue analysis, it's essentially eigenvalue analysis. It's an eigenvalue analysis of variation of the data set. And most of this remains as future work. But I will say that so far I have collected an average strains on the free wall and on the septum. I want to do it for the 15 region model in the future. And the statistics that I perform are fairly straightforward right now. I just am looking at ANOVA because I have 3 groups that I want to assess differences between. And I look at associations with 2D measures where I correlate what I have just done with existing measures. And why do I do that? Because when you're introducing a new measurement, whether it's to clinicians or to anyone else, the first questions most people ask is, well, how does it compare to what we've done before? So you can do that with a correlative analysis. You can also do that with a technique called finite-element, which I do not have in this presentation today, and I apologize for that because that is an important part in comparing a gold standard to a new technique. So my additional analyses in the temporal domain is once I have these regions, I'm going to create strain time histories. So that is to say, I want to track strain as a function of time in each of the regions, and I will get these curves. And then I will use PCA to see how these curves, these time histories, change across patient sets. And then future work is saying, I've got these new measures, how well do they predict patient outcomes? And that is to say, if I do a measurement today, do they predict whether or not the patient's disease will worsen in a year or 2 years? Because if we can predict the future, then we can try to prevent it through, again, increased therapy or other interventions. Okay, so I've introduced this cohort. It's a cohort of 172 kids in 3 groups: my control kids, kids with associated pulmonary hypertension, kids with idiopathic pulmonary hypertension. And I'm here to tell you that my new measures are, their means are very, very different across the groups. And, you know, you can say, what's the difference between different and very different? If your p-value is a measure of just how different things are, I'm getting some extremely small p-values. And the p-values are quite a bit smaller than anything I get from existing 2D data. So what clinicians look at today are a measurement called TAPSE, or tricuspid annular, what is the P again? Tricuspid annulus plane systolic excursion. That's a long word, but more or less what it means is that the tricuspid valve in the right ventricle, it moves longitudinally when the heart contracts. And if you track that movement, you get TAPSE. It's got a much more complex name than what it is. And it's different between these kids at a p-value of 5 × 10⁹. And this GLS is global longitudinal strain, and FW is of the free wall. That's different. GLS, or global longitudinal strain of the septum, is different. And ejection fraction is another clinical measure. It's just what percentage of the volume that was in the heart at end diastole has been ejected by end systole. And it's a measure overall of heart efficiency. So all these are different. All the measurements that we currently make are different, but none of them are quite as different as the new global longitudinal strain that I'm measuring, or the maximum principal component magnitude of strain that I'm measuring. And I don't know what to say about that yet, other than the p-values are quite a bit smaller. We'll see. I hope that means they'll be more sensitive predictors, but I don't have evidence of that yet. I just have very strong evidence that they are different, that the means of the groups are quite different. And then I'll point out, I get the principal component angle. So that is to say, if I look at a principal component of strain, its direction is given by the strain state. It's not defined by where the head to feet axis is, or where the circumferential axis is. It's defined within the measurement of strain. And it is different between control patients and pulmonary hypertensive patients. And indeed, pulmonary hypertensive patients have principal components. Their maximum principal component of strain is 12 degrees more directed in the circumferential direction, which is what I would expect if these kids' hearts are remodeling, and that remodeling makes their hearts contract more circumferentially. So that's a really nice validation of this technique, is that it's providing information that 2D strain simply cannot provide. Finally, and this is beginning to look at how does this compare to what's been done before, I look at my 3D free wall longitudinal strain. So this is what I'm computing. And I compare that to 2D free wall longitudinal strain, which is the strain you can get from a 2D echo image. And they're fairly well correlated. And that is what I would expect. And then I can also look at these longitudinal strains on the septum, and I find that they also are in fairly good agreement, or they're fairly well correlated. I won't say agreement because that's what a Bland-Altman plot checks. And then finally, I'll look at the maximum principal strain, and that is actually has the greatest correlation with the 2D free wall longitudinal strain. What that means yet, I'm not sure, but more or less, I am measuring something that is similar to what has been done before, but I am hopeful that it does provide more insight into heart function. And that's about it. I mean, the title of this slide is "There's Always More to Do," because there is, isn't there? And my number one thing to do is to get this published. So Priya has continued to work with me, and I'm grateful to her that she has worked with me to get this paper together. There's just a couple more things that we need to do to get it out. Hopefully it'll be in submission before the end of the month, maybe even before Thanksgiving. And then I will continue on in my development tasks for AIM 2 and 3, the things I had as future work. I'll apply it to a larger patient set. And then eventually we'll look at patient status and composite disease outcomes, which is to say, we'll see whether or not this is a more sensitive measure of right ventricular function. And like most people, I don't work alone. And these are all the people that, well, the slide says it. These people are totally amazing. These people have helped me do this. Some of them have helped me do this. Most of them are people that I've just worked with over the years, and I just keep on this slide because I have gratitude for them that they have helped me in my career. But in particular, this one has Pene and it has Priya. So thank you. That's all. Questions?
Thank you, Kendall. That was a great presentation.
Thank you.
And we open it up. I think Dana has a question. I just saw his mouth moving. Do you have a question?
Yeah, thanks, Kendall. That was really cool. I'm used to looking at FEA of bones, and it's so cool to see other applications. I have a question, and this is partly due to I just don't know that much about remodeling of the cardiac wall, but So it just happens last week I gave a lecture in my biomechanics class about the heart, and I showed them how as you go through the thickness of the wall, the muscle fiber direction changes so that like it squeezes in all different directions, which I think is a super cool mechanical part of our body. But so if the heart adapts to do more circumferential contraction, do the layers that are not in that direction kind of start to change their orientation, or is it like more, would you think, hypertrophy of that layer that's got them like in the circumferential direction?
Dana, that is like an awesome question, and it just shows you know a lot more about this than you just said you did. And the answer is that we're not sure yet. The most recent paper that I've seen on this is actually a paper by it's by Mark Simon, actually. So he's on here. He's at Pittsburgh, and Mark Simon he extracts heart tissue from, I think he's mostly doing rat hearts in pulmonary hypertension, and he puts them on a biaxial tester. So he's using the biaxial tester to see the strain patterns, and then he does histology in order to detect fiber directions. And if I remember correctly, I reviewed the paper like a year and a half ago, and it didn't get accepted, which I thought was terrible because it was a difficult and challenging work, and he was showing some interesting things with it. But he was showing that it was the remodeling process. So the part of the heart that was growing during remodeling was in the remodeled direction, but there also was some fiber alignment within the deeper tissues. So I guess the answer, as far as we know, is both are happening. That's the best we know right now.
Yeah, thanks.
So Kendall, could you apply this to, further out on the arterial or venual aspects? Anything that is there any other areas where, I know it's not muscular bound, but are there other areas where this could apply, or other organs or other?
You could.
Outside the heart?
Sticking within the heart for now, I'm going to say that magnetic resonance imaging can also provide these meshes. It's a bit more complicated, and the temporal resolution isn't as good, but I'm interested in looking at this on the left ventricle as well. So that's there. I don't know whether or not it would be useful. I mean, other vessels, I can only speculate. I guess it would depend on how much their function is dependent on contraction. Mm-hmm. I have already done vascular strain, so that would just be purely circumferential strain of a vessel. And I've done that to show that vessels stiffen in disease and try to assess that stiffening as a diagnostic of the disease process. But that was actually much simpler because you can just look at change in diameter. Essentially, change in diameter using an echo modality can tell you how much the vessel is straining. If you assume it's a circular vessel, which isn't quite true, but we're engineers here, so we approximate stuff. It's close to circular. Huh.
I was thinking like lungs and other things where there's.
Wow. Potentially, yes. So Brad Smith in bioengineering, he's really looking at how the lungs are stiffening, mostly in childhood ventilation. But he is modeling that stiffening at the alveolar level, so at a microscale level. But certainly, if we had, for instance, an MR of the entire lungs, we could look at surface. We could look at surface strain. We would need to get. It would become much more complicated if we were going to start to look at actual volumetric strains within the lungs, but it could be done. It'd be fun.
I'll ask another question. Come on, people. We got some good questions, I'm sure, out there. Where do you think you could take this visually?
Wow. So I think the best way I can answer that is, and it was really, so let's talk about one of the first ways we thought about this. And the way we first thought about it is before we had any of AIM-2 done, before we could really speak to how to average strains on particular locations, we just looked at these meshes and we started to notice, hey, we expect this longitudinal deformation, but we're getting more circumferential deformation on the diseased hearts. And Priya actually, I produced a set of 30 blinded meshes, and Priya then analyzed these 30 blinded meshes. So she didn't know whether they were sick or healthy. She just looked at the deformation patterns and she said, okay, that looks more longitudinal or more circumferential. And based on that, she said whether or not the patient was sick or not sick. And it's telling that she got 27 of 30 correct.
Wow.
So in other words, just looking visually at these meshes and how the strain patterns changed was telling us whether or not they were diseased. So that was, go ahead, sorry.
No, I was gonna say, I know you said you're looking at this longitudinally, and that tells me that's gonna be a really interesting thing too. How does this change over time as somebody becomes more sick? I never say sicker because, it's my name. It's one of those things. I imagine you're gonna, as you collect data over time with this, you're gonna see all sorts of interesting things come out of it, where there's more or less change occurring. Should be.
That is exactly right. That is my hope.
And Tom Altman and I were chatting on the side that we've never heard of this town Pittsburgh without an H. We just want to call you on that. So we're both Pittsburghers, so we take offense when we spell our city wrong. So
oops. I'm an engineer. My pronunciation of English and spelling of English are terrible.
Any other questions? We're over time, but I'm happy to open it up for one more.
Well, I have a quick question.
Hey, Kelly.
Hey. So I was interested about how you're partitioning these by curvature. Are you measuring like the scalar curvature, or are you measuring like the full three-dimensional curvature?
It's the maximum curvature at a point. So it's like the area, it's like the steepest descent, more or less.
Oh, okay, cool. Thank you.
Mm-hmm.
Very cool work. So did you say that this was essentially a master's thesis or a PhD thesis? Because this, maybe she deserves another degree.
Hey, if Priya's on, she can come in and can complain that I didn't give her enough for it. This was Priya's master's thesis.
Nice work, Priya.
Thank you.
Any other questions?
Priya's looking to get hired, everyone. So if you're hiring, you should hire Priya.
There we go. Dana nodded.
All right.
Okay, well, this was really great, very interesting, and it's so cool to get to know your work. Obviously, we've been working together on other things, but I've never really known what you've worked on. So really enjoyed it. Thank you so much, Kendall.
Thanks, Doug. Thank you, everyone, for attending.